course, the RP2040 has two cores. That's the meaning of the 2 in the 2040 name, and the 0 is the Cortex M0 Plus, so it's got two Cortex M0 Plus cores. Here they are referred to internally as Processor 0 and Processor 1, and via the bus fabric they can communicate with memory, external peripherals, the GPIO pins, that kind of thing, and they are linked to each other via something called the SIO, which is the single cycle I/O block. The SIO contains various mechanisms that enable the two cores, the two processors, the two threads, if you like, to communicate with each other. And first off, we've got two FIFOs, and each operates in a single direction. For the first one from core 0 to core 1, and the other one from core 1 to core 0. And these are first in, first out buffers. So you can pass data between the two threads, and each thread or processor or core, I'm using those terms interchangeably, can either poll its FIFO to see if anything's arrived, or you can trigger interrupts on them. And the other mechanism is hardware spin locks, and a spin lock is a way of protecting memory variables from race conditions where two processes, threads, call them what you will, try and access the same memory variable. So a thread operating in one core can lock a memory variable, can acquire a spin lock, and whilst it writes to a memory variable, and the other core can respect that spin lock before it reads from the memory variable. When code starts executing on an RP2040, it does so on core 0, with core 1 sitting idle. So to date, everything that I've written is just executing on core 0, and we've got another core just sitting idle, waiting for something to do. And it seems criminal, really, not to use it. You have to physically launch code on the second core, core 1, which you do by calling a function called multi-core launch, strangely. I need to decide which functions or what code I'm going to run on core 1. Obviously, when the program starts, it's going to start executing on core 0, so main is going to be on core 0. But once I've set everything up and I've triggered the DMA channels to get audio in and out, I then sit in a loop in main, just basically polling the user interface devices. That's the potentiometers for feedback and wet dry mix, that kind of thing, switches, and I'm signaling to the function that processes the audio what it's supposed to do, what its delays are, etc., by using global memory variables. And global memory variables will still work between the two cores. I might need to protect them by spin locks, but it's simpler if I don't. And so what I'm thinking is that I'll launch core 1, the second core, and it can do that boring polling the user interface stuff and updating some global variables, leaving core 0 to concentrate on the more real-time stuff, the audio processing, DSP, that kind of thing that we'll get into in the future. So the code running on core 0 boils down to main, which is called when the program loads, the DMA interrupt handler, which is processing incoming and outgoing audio data, and my process audio function that at the moment is running my little delay and feedback algorithm. But there's one other function here, which is check reset, and that's because in this, when you press the rotary encoder switch, I want to save and disable the interrupts that are being called to stop the DMA data stream running whilst I clear the memory out. And my understanding is that you can only disable and re-enable interrupts on the core where the interrupt handler is actually running. And because my interrupt handler is running in core 0, that's where I need to do the disabling and re-enabling of the interrupts. So my main function does some setup, sets up some of the pins, sets the read and write pointers to the buffer, and launches the DMA process, and then it calls this multi-core launch core 1, and it passes it a function called core 1 entry, and then it sits in a loop where basically it's just polling that that reset button until somebody comes along and clicks it. For my own clarity and ease of management, I've created a new C module that I've called Parrot Core 1, and this is all the stuff that's going to be running on Core 1 as opposed to Core 0. And so in here I've moved the functions that poll the feedback potentiometers, the wet dry potentiometers, that kind of thing, and it contains this function called core 1 entry that's called from main that's operating on core 0. And so this kicks off the second thread, for want of a better name, the processes that run on the second core of the processor. So this is going to run completely independently of what's running on core 0. And so it goes through its own setup, setting up some of the GPIO pins that it's going to use. That's feedback, wet and dry, moving average buffers, that kind of thing. And then it sits in its own loop, just polling the potentiometers and checking for user input, and then it's going to communicate with core 0 at the moment just by using global memory variables. I'm going to set delay values as a global memory variable, and core 0 is going to read that, and I'll worry about needing spin locks later if I come across things like race conditions where they're both trying to read and write from the same memory variable at the same time. But we'll see. And you know, in future I could use the FIFO buffers to offload some of the DSP from one core to the other perhaps, but at the moment I'm just going to put slow polling type functions to run on core 1, and I'm going to keep the faster DSP audio related functions on core 0, and I'm going to use that as the logical split between the two cores. The question is, what difference has splitting the code to run on the two cores made to the Camberwell Parrot as it currently stands? And the answer is no difference whatsoever that I can notice. Everything's still working exactly the same. But I guess we've doubled our processing bandwidth, so that's pretty good then.